Hello everyone, I'm Ekin Gürhan. Right now I'm going to talking about space navigation. So let's start. What is navigation? Navigation is the art and science of determining position, planning, and following a path to reach a desired destination. It is essential for safe and efficient travel, whether on Earth or in space. Navigation has evolved through four main domains: terrestrial, maritime, aerial, and naval-space. While early navigation relied on position of the stars and compasses, space navigation integrates advanced sensor and autonomous processing to manage positioning across vast distance, the core purpose remaining the same, determining location and reaching a target accurately. In the before the century or after the century, where is not advanced technology exists in history, uh, especially in the night, the sailors don't have any access to lights. They just only use candlelight. So, but in that time, the sky is very clear. So they are built map or campus or any related to navigation system to find their way. Space navigation from ancient tools to modern system. Navigation has evolved from guiding ships across vast oceans to plotting courses through the cosmos. This presentation explores the historical roots, technological milestones, and cutting-edge systems that make precise space navigation possible. Understanding the navigation, historical process. Navigation involves determining position and planning routes to reach destinations safe and efficiently, as we say. Historically, navigation began with maritime methods using celestial observations. Ancient sailors depended on tools like astrolabe or sextant to locate their position by the stars. Celestial maps helped early explorers understand the night sky patterns, enabling accuracy sea travel long before modern technology. And if you look at the sky, uh, you cannot any changes during the night. So the one of the really reliable navigation system in that time is the observing the uh, celestial bodies and uh, with that with using the stars orbits or some asteroids even they build some maps using the astrolabe and sextant. And after that, of course, the rise of the space navigation. Space navigation emerged alongside early rocketry efforts. The Cold War suffered rapid advancements during the space race, leading to landmark achievements like the launch of the Sputnik and Explorer, the first artificial satellites. These satellites pioneered orbital positioning, laying the groundwork for continuous observation and navigation beyond the atmosphere. These two satellites uh, lead the United States or Russia to build more space, build more satellites, and because in that time the United States and the other nations are afraid of the other side can build a spacecraft that observe everything around in the surface and maybe some weaponized by the in the satellite and launch to um, any country. So they try to build immediately new satellites. So first is one global navigation satellite system, GNSS. The global positioning system GPS is the one of the belongs inside the GNSS. Launched by US, revolutionized navigation with precise location data, especially for low Earth orbit missions. Other GNSS, including Europe Galileo or Russian GLONASS and China's Beidou, provide global positioning services. Together, these systems enhance accuracy and redundancy for space missions. GNSS systems like GPS work efficiently in low Earth orbit, but their signals become too weak for use deep in space. CubeSats and LEO satellites can utilize GNSS data for onboard autonomous navigation, but deep space missions require alternative methods. Core space navigation system. Space navigation relies on several core systems that ensures precise positioning and guidance across vast distances. This system combines advanced technology and proven principle to support mission from low Earth orbit to deep space exploration. Before exploration, internal navigation system, it is important to understand the foundational core navigation system and how they integrate to reach the highest level of accuracy and reliability. Why do we start with inertial navigation system? Because one of the first navigation system built in the space area, mostly in that time, mostly contained mechanical parts. So INS technologies uses accelerometers and gyroscopes to track an object's velocity orientation without relying on external signals. This self-contained system is crucial for space probes and spacecraft operating beyond GNSS coverage, enabling continuous navigation through precise movement detection. And after that, second, they built optical navigation. Optical navigation leverages onboard cameras and to identify celestial bodies and landmarks, determining spacecraft position relative to these reference. These methods support autonomous navigation by comparing observed images to reloaded star catalogs or surface map data, essential for planetary approaches and landings. Optical navigation was used in missions like NASA's New Horizons, when spacecraft relied on the visual data to align its path during the Pluto flyby. Of course, for optical navigation, the autonomous part is uh, i- improved in later time. So the third one is the celestial navigation. Celestial navigation in the space extends the age-old process of using stars for positioning. Star trackers identify fixed stars that establish spacecraft orientation. Modern spacecraft utilize highly sensitive star sensors and enable precise altitude determination by analyzing star patterns, critical for mission stability and direction. Of course, all of them is the core of the navigation system, but none of them work alone efficiently because we need to combine all of them because the missions related to space are very expensive and some of them includes also humans. So any mistakes you can make, any mistakes navigation system make can cause very serious damage. So hybrid navigation system. Hybrid navigation integrates inertial, optical, and celestial techniques to overcome individual limitations, ensuring robust guidance across diverse mission scenarios. By fusing sensor data and algorithm, hybrid system enhance reliability, accuracy, and enabling humans ambitious ventures further into our solar system and beyond. Of course, with this system, we need to upgrade this system. So, navigation, software, and algorithms. For example, extended Kalman filter, core algorithm for integrating data from images, star trackers, and optical system, enabling precise navigation estimation. This is used mostly in the optical navigation system, and it can be when you take the picture, it can be more when you filtered with Kalman filter, you can see more and more uh, stars or planets in the pictures. Navigation grade and versus tactical grade images. High precision images target deep space missions. Tactical grade images unites rely on redundancy and error corrections for reliability. Uh, Open loop versus closed loop architectures. Closed loop systems use continuous feedbacks to self-correct, enhance accuracy over long duration missions. Actually, the closed loop most likely using space area because its system has to correct itself. If there is any error or any uh, bad decision to make as a navigation system, it has to be correct itself. And also another navigation software or algorithm is autonomous path planning. Advanced algorithms enable spacecraft to dynamically compute optimal trajectories, adjust to real-time changes, and avoid obstacle while conserving fuel. This is something like we can say that like we have in the world we have Google Map, and in the Google Map you can go anywhere you want, creating a new path that in 2D. But imagine you can have a Google Map, something like Google Map, but it doesn't show the Earth surface, it shows the solar system. So this is a futuristic one, actually, but in the future, uh, they will build something like it, and we're going to, for example, to moon more easily. Adaptive algorithms, leveraging machine learning and AI, these algorithms empower navigation systems, learn from mission data, continuous enhancing accuracy and reliability. Actually, if you look at like 10 years ago, there is no sign of any AI, but right now AI is very important role in our technologies, and in the future, probably it will take everything from us. And if we use in the spacecrafts navigation systems to, in AI, it will get and correct itself automatically. So it's a very, very advanced and very good our navigation systems. Right now, deep space navigation. Right now, we are using the deep space network. And what is the deep space network? Is a global array of large antennas that provide tracking, telemetry, and command services for spacecraft exploring the far reaches of the solar system. Utilizing precise radio signal, the DSN measures spacecraft distance and velocity, enabling accurate position estimates millions of kilometers away from Earth. While DSN provides two-way radio tracking for deep space missions, alternative like one-way Doppler and onboard epimeris propagation are used when communication is delayed. Actually, right now, if you can see the right top, there is a three main antenna for this navigation system, and this is Earth-based navigation. And in the bottom picture, you can see the angle that covers to space. These three of them are actually reducing the error. First one is the radio tracking. Radio tracking uses large antennas to communicate with spacecraft, sending and receiving signals that reveal precise spacecraft location and trajectory. Ringing measures the time delay of radio signals to calculate distance, while Doppler shifts determine velocity by analyzing frequency changes, enabling accurate real-time navigation updates. These techniques form the backbone deep space network missions, guidance supporting spacecraft far beyond Earth's orbit with continuous reliable telemetry. So these are the create reliable uh, resources and reliable telemetry to our finding our uh, position of our spacecrafts. Of course, there is some passive navigation techniques. Not all the space navigation depends on the active tracking. Passive techniques can provide position estimation by observing celestial cues or natural orbital effects, especially when communication is limited or delayed. One of them is the gravity assist. Fly by after spacecraft trajectories and verify position using orbital mechanics for trajectory corrections. And the second one is the sun angle shadow orientation. These cues guide spacecraft descent and approach when the active sensors can be fully trusted. The third one is the occultation timing. tracking when a spacecraft passes behind a celestial body, refines orbit models without active si signaling. This is mostly used when for example, satellite, for example, lunar mission, you send a space satellite around the moon, but when your satellite goes to the dark side of the moon, it can be cause some delays or some misconnection with them. And if you create a navigation system as a passive, you can already estimate it where is going to be, what is the path of the satellite, and you can easily track it. Right now, modern navigation techniques in space, onboard autonomous navigation, enabling its spacecraft to independently determine their position and trajectory without relying on Earth-based tracking, combines sensors like inertial measurement units, star trackers, and cameras to continuously compute accurate navigation data in real time. This autonomy is crucial for deep space missions with communication delay and for precise maneuvers such as planetary approach and landing. Actually, yes, right now we have used the DSN, and but for the further away, like go to the Mars or even the Moon, we have some autonomous navigation system. So one of them is the autonomous optical navigation system, and this system is still improving. Autonomous optical navigation enables spacecraft to determine their location and the trajectory independently by analyzing images of celestial bodies and star fields. This method merges advanced onboard imaging with powerful process algorithms, allowing precise navigation without constant communication with Earth. Crucial for missions in deep space, autonomous optical navigation reduces reliance on the Earth-based tracking and supports fast decision making during the complex maneuvers. This is more likely it takes the picture itself, and in the system there is the data already taken by Earth-based data, and it measures itself the location or speed or whatever we need. Also, another techniques is the SLAM, simultaneous location and mapping, enables spacecraft to build maps of unknown environments while tracking their own position within them. Essential for surface exploration, SLAM supports rovers and landers navigating dynamically on planetary terrain by integrating sensor data from cameras, lidars, and inertial units. SLAM provides real-time awareness critical for autonomous operations in hazardous uncharted location without GPS. Of course, this SLAM technologies or other technologies or other navigation technologies are not used a based one. The base one is still is the Deep Space Network, but also in a second plan they're using another system. Real-world navigation case studies explore how advanced navigation technologies are applied in background space missions. For example, for Mars rovers, SLAM and autonomous optical navigation enables rovers like Perseverance to traverse challenging Martian terrain safely and efficiently, continuously mapping their environment. Of course, we have a lot of satellites around Mars, and also we have like Google Earth and Google Earth, like we have Google Mars. You can see everything in them, but it is not interact like us. Like when you put, for example, Perseverance in the Mars surface, it interacts still with surface. So it has to be a different navigation system that correct way because there is no road in the uh, Mars. So you have to put some navigation that detects some rocks or some stones or some sand wind, some storms. So you have to use a different navigation system. For Voyager provides radio tracking and Doppler techniques from the Deep Space Network have guided these probes across the outer solar system and beyond for decades, maintaining critical communication. A Voyager built very long ago, like 1971, In that time, there is only just very uh, based navigation system. So it only used deep space network and some algorithms to communication. And also, I think the one of the Voyagers right now left our solar system. So it is a very millions of kilometers away from us. For the new missions, for example, Artemis lunar missions, a hybrid navigation system combining inertial, optical, and GNSS technologies ensure precise lunar landing and surface operations for the Artemis missions for future exploration. Of course, we can use in for a moon. We can use some DNS, DSN, GNSS, but we have to create own lunar-based mission, navigation system. Iconic space navigation missions. I'm not going to talk all of them. You can investigate each of them. But I want to point out one of them, is that is NASA Lucy mission. Right now is the active mission, and it uses autonomous navigation to explore Trojan asteroid, studying early solar system remnants. It is normally used in the investigate the Trojan asteroids, but it's normally used DSN, Deep Space Network, but also they added some optical navigation system. Maybe they added an autonomous optical, and they try to uh, measure its location, velocity, or other stuff. And when it's near to the asteroids, it tries to take a picture and try to calculate its own location. Planetary surface navigation. Exploration vehicles like Mars rovers rely on integrated navigation approach to traverse challenging and unknown terrain safely. Visual odometry. Using cameras, rovers continuously capture images to estimate movements by tracking changes between frames relative to surface features. Inertial measurements. EMUs measure acceleration and angular rates to provide short-term position and orientation estimates, complement visual data, and this is for actually mostly rocks or uh, other things that maybe a rover cannot go through. So it's calculate before and changing to its path to different way. Beacon-based localization on Mars. First one is rover orbiter comparative tracking. Mars rovers use signals from orbiting satellites to improve navigation accuracy. This cooperation helps pinpoint rover location in challenging terrain beyond the visual of line of sight. Actually, this is one is using right now because there is some satellites around the orbits in the Mars, and right now the Mars rovers communicate with them, and that send us the data. But of course, the second one, beacon network for localization. Radio beacons placed on Mars serve as fixed reference, allowing rovers to triangle their position with higher precision compared to visual method alone. Actually, this is a bit futuristic. As I say in the moon-based navigation, we have to also build a Mars-based navigation system if you want to colonize the Mars. As I said, lunar navigation system. Right now, the humans start to Artemis program, and after that, they probably colonize the moon. And of course, moon is a bit closer to Earth, but we have to build some navigation systems. It can be, is symbolized in here, can be ground-based system or orbiting base. It depends on the situation, of course. But if you want to build a building in the and uh, put more rover in the surface of the moon, we have to build a lunar-based navigation system. Space telescopes and observatory navigation. Of course, there is not only satellites in the space. We have a different or some of a few of telescopes or observatory satellites. And space telescopes and observatories utilize precise navigation systems to maintain stable orbits and accurate pointing towards distant celestial targets. Advanced gyroscope, star trackers, and reaction wheels work together to control orientation and compensate for external disturbance like gravity or solar radiation pressure. These navigation technologies enable continuous observation of faint and distant phenomena crucial for astrophysics, cosmology, and planetary science. Examples include the Hubble Space Telescope, fine guidance sensors, and James Webb Space Telescope integrate control systems. These two actually is the most popular, the Hubble Space Telescope and James Webb Telescope, and these two are very far away from the Earth, and that's why you have to put very advanced and good navigation systems to get from data from these satellites. High precision attitude control and optical tracking. Maintaining its exact spacecraft orientation is crucial for mission success. High precision attitude control system utilize a combination of gyroscopes, star trackers, and reaction wheels to stabilize and adjust positioning with exceptional accuracy. Ground-assisted optical tracking supplements onboard sensors by using Earth-based telescopes and laser radar. These cooperations enhance navigation precision, allowing real-time adjustment and reliable spacecraft positioning, especially during critical maneuvers. And even if here, as you can see, not you cannot use just one navigation or uh, one system in the navigation system. You have to use multiple system in the navigation. Emerging navigation technologies, X-ray pulsar navigation, aka SNAV. SNAV leverages the precise timing signals from pulsars rapidly rotating neutron stars emitting X-rays to determine spacecraft position autonomously in deep space. By detecting these natural cosmic lighthouses, spacecraft can triangle their location without relying on Earth-based signals, enhancing navigation accuracy for future interplanetary and deep space missions. Of course, these technologies are very futuristic and still developing time to time, and also this can help us. For example, you put a satellite very near to sun, and there is some explosion at the sun. You can calculate the dangers of the wave, can reduce X-ray or uh, other stuff, and you can get uh, a solution before you have faced of the that wave, for example. Emerging autonomous navigation technologies. First one is the autonomous smart navigation. Group of small satellites like CubeSats coordinate autonomously in real time using onboard sensors and AI. This enables highly resilient and adaptive missions through co collaborative navigation and obstacle avoidance. NASA's Starlink mission, uh, Starlink also actually belongs to the SpaceX, is a prime example where CubeSats communicate via inter-satellite links to dynamically adapt their position, offering a scalable model for future planetary exploration. It's there is a website and it shows us all orbiting satellites around the Earth. And if you can see that there is a lots of satellites, and most of them using the for navigation system. The second One is the AI ML enhanced predictive navigation. Leveraging machine learning algorithms, this technology analyzes vast data streams and precisely forecast spacecraft trajectories, optimize routes, and autonomously fine-tune navigation parameters. This results in significantly improved accuracy and operational efficiency for complex missions. This is exactly what I said actually. The AI is very important for our future navigation system. We have to integrate both all of them together. Challenges and future prospects. Current limitation in space navigation. Space navigation faces difficulties such as signal delays over vast distance, limited onboard sensor precision, and dependency on Earth-based support. Deep space missions struggle with autonomous localization and maintaining communication links. Future advances aim to enhance autonomy, accuracy, and resilience by integrating AI, quantum sensors, and new navigation paradigms, including pulse-based and swarm technologies. Uh, Also, for example, for the DSN, there is lots of satellite around Earth, and it can sometimes cause the DSN overdrive, and that caused some delays and some errors can be happen in the navigation system. Also, for example, in the around, for example, the far beyond the Mars or far beyond the Pluto, it's very far away from Earth, and the getting signal from there is too much take time. And in that time, your satellite or your spacecraft already moved to a different destination. So if its own navigation system, if it has an own navigation system, there is no need any delay or error. Navigation needs of future missions. Future missions demand ultra-reliable autonomous navigation system capable of operating independently far beyond Earth's reach. These missions require real-time decision-making, adaptability to unknown environments, and integration of novel sensor technologies. Key challenges include mitigating communication delays, improving deep space localization, and enhanced resilience against sensor failures and cosmic interference. Addressing these issues is critical for safe, efficient exploration of the outer planets, asteroids, and interstellar space. Why navigation matters? If we sum up, mission safety, human exploration, autonomous operation. Uh, for mission safety, as I said, the missions are very expensive and some of them rely on humans. So we have to put very advanced and very reliable navigation systems. As a human exploration, we love to explore space. And right now, mostly we are exploring moon base and Mars base. But in the future, there are some another missions like mining missions. Right now, we're using minerals to create new things. But in the future, there will be need more different materials. So how can we get that from, for example, asteroids? But asteroids are very small when you compare it to moons, especially. Even planets, they are very small. So if you have a very good uh, navigation system, you can go easily to asteroids. Also, autonomous operations, of course, that includes everything. Oh, but for example, in the Mars surface, you have a rover and you have to have a autonomous operations, autonomous navigation system that corrects itself and uh, find its own way. So, reliable navigation is the foundation of successful space exploration. Without it, even the most advanced missions become blind. Conclusion. Reliable navigation is the backbone of every successful space mission, from orbital stability to precise landing. As we reach farther into the solar system, autonomy and redundancy and real-time decision making will become non-negotiable features. Advancing navigation technologies will unlock new frontiers in exploration, enabling more autonomous, efficient, and resilient spacecraft operation in increasingly distant and complex environments. And this is my reference. Thank you for listening to me.